Welcome, and thanks for attending ChromeOS Video 101, also known as Life of a Video Frame. My name is Miguel Casas, and I'm a software engineer right now in the ChromeOS graphics team. I joined over 7 years ago in Stockholm, Sweden, in the WebRTC team, and I've worked for video capture and different web APIs related to it, like media recorder, image capture, and about 3 years ago, I joined ChromeOS Graphics, especially working on video, all things Chrome, with an emphasis on Chromium OS. Mhm. So in this talk, I'm going to talk a little bit about presenting a helicopter view of how video is decoded into video frames, and there you go. How the video frames are decoded, are composited, are rendered, and presented to the user, how we use accelerated video decoding on Chromium OS, and how video playback ties with the graphics stack, the whole composition, and the GPU acceleration. A note is that in these slides, when I say Chrome, I could say Chromium perfectly. We tend to talk about Chromium, Chrome, Chrome OS. Everything is interchangeable for the purpose of these slides. Everything is public, everything is open source. So yeah, this slide has a helicopter view of how video decoding works, how video playback works in Chrome, sorry. So when a video tag element is loaded into Chrome, network packets start being received by the network stack. Somehow this is magic, it's not the topic of this talk. These packets contain bits and pieces of encoded video and audio that are transported in a container, which adds, for example, timestamps, or more esoteric things like subtitles and whatnot. These network packets are reassembled and they are fed into a demuxer. In the render process, this gray area here is all in the render process. This demuxer separates it into encoded audio and encoded video. Each one of those encoded video things are called usually chunks, and so are the encoded audio ones. Each encoded chunk is then decoded into either audio buffers or video frames by means of the video decode and audio decode entities. The video frames themselves, so they are decoded 1, 2, 3 in time. They are sent to these out of process entity that is called the V's or the GPU process, where they are composited with the rest of the layers of the web page and with the whole of ChromeOS UI, and then they are presented to the user in their screen, hopefully. The audio buffers, in the meantime, they are sent to the speakers of the system or whatever other audio device that the user has connected, and they usually clog the whole playback. There's many more audio buffers than video, so basically as the audio starts coming out, the renderer will start sending video frames out. This diagram, this helicopter view, applies with minor variations to video on demand like YouTube and Netflix, and real-time video, like for example WebRTC, Stadia. They work in similar ways. So how does video decoding work? Video decoding obviously is a very complex topic. So I'm going to try to explain the absolute minimum needed in 2 minutes to get the ball rolling. Everything that goes into this video decode is codec specific. You might have heard of VP8, VP9, AV1, H.264. There is a talk, maybe in this Chrome University, maybe in the previous one, titled Life of a Codec that I recommend you watch to learn more about how they are created and designed in their lifetime. Anyway, so all popular decoders work a bit like that. First, we receive a single chunky frame that is pretty much like an image. It's encoded, it's a standalone image, for example, similar to JPEG. And this is called normally keyframe or intraframe. Video decode gets it, decodes it, puts it somewhere. The next frame that we receive is constructed by differences with the previous one. So here the Pac-Man move a bit to the right. The way the video decoder will store these differences is by figuring out where the different blocks of the image have gone to. Because of this second frame is called sometimes delta or interframe. I'll use interchangeably those two names. Well, after this second frame, this interframe has been decoded and has probably been stored somewhere. The next frame is another delta frame. all of these new frames from this point on are constructed referencing previous frames, typically one, but sometimes more, that are before or after. And all those frames are called reference frames. This form of compression is great because video sequences have a lot of temporal redundancy, and like images tend to look very much alike from one moment to the other. So that's called temporal redundancy. This type of encoding is great for bandwidth, but it's a bit bad for delay because before producing any delta frame, we'll need to decode and store somewhere all the previous reference frames. Again, this is a very crash overview. It's a huge topic, but I just wanted to introduce um, a bit what is needed to know for the rest of the discussion. Um, some topics to bear in mind is that keyframes are great because they can be decoded immediately, but they are pretty huge. They are good for real time. They are very large, bad for bandwidth. And another note is that in a normal stream, we'll receive one keyframe and very, very many predicted frames or delta frames, like I call them. That's great for bandwidth, but if in any of these intermediate decodings there is an error, it will tend to accumulate, and then you see all these artifacts like blockiness or green colors coming here and there until we get another keyframe that can kind of like pave over all those errors. So still talking a little bit about video decode. In a simplified view of the world, video decode is done in software. So that's it. There's a third-party library. In the case of VP8, VP9, we use this guy here, VPX codec decode. So this is a screenshot taken directly from the code we use on Chrome right now. It's entirely inside the render process, which is great because it's sandbox. So if something goes wrong, it will be very isolated. The output of this video decode will be found, these video frames that I draw here, they will be usually on CPU-bound memory, for example, shared memory. More topics. The video frames themselves, they typically come up with a presentation timestamp that, as I said, it comes from the container. So basically says these video frames should be represented at 0.16, 0.016, this one at 0.033, etc., etc. So it has to be like super fast. If for any reason that the code takes more time than this sequence of timestamps, then we start having things like drop frames and jitter and playback hiccups and in general bad things that users tend not to like at all. Another note in this case is that if this was a real-time communication, usually these timestamps will not be present, and we just want to play back as fast as we can, because the whole clocking of the system happens at the other end, at the encoding end. Okay, so now we have this series of decoded video frames, and what happens now? We have to basically put them on the screen somehow. And for that, what we have is the Chrome Compositor, that is also called System Compositor or Display Compositor. Is a subsystem here in the GPU process that we mentioned before that, again, takes all these inputs like the Chrome UI and the layers of the screen and all that stuff. There has been another talk yesterday morning, I presume. It's called Life of a Pixel. Super important. This is basically how all these items that are called compositor frames are created and sent to the video, to this GPU processor. Anyway, so this system compositor gets all these inputs, and what it does is to create and enqueue commands in some rendering API, for example, OpenGL, Vulkan, Direct3D, to produce the next frame buffer. These commands, like do this, put a little bit of a texture there and stuff, they have to refer to platform-specific GPU resources, because in the vast majority of cases, we have GPU accelerated rendering in Chrome. Those GPU resources can be, for example, images, can be font atlases, can be, of course, a video frame. And these GPU resources are basically sitting on the critical performance path of Chrome. They have to be manipulated at maximum speed with no delay at all, and many, many engineering hours go into optimizing their use in all platforms. Video frames in particular are usually uploaded ahead of time to this GPU accessible memory so that whenever the system compositor needs to access them, they are ready to go. So yeah, the system compositor uses the GPU, generates an X-frame buffer, and then the frame buffer gets displayed on the screen on the next vsync interval, hopefully. And that happens up to 60 frames per second, the famous 60 hertz of the screen. Note that we have not used at all any hardware decode acceleration. This is all just GPU accelerated composition or GPU accelerated rendering. Oh, okay, that was that. Somehow part of the screen didn't show up. So the graphics bandwidth, what I wanted to mention here is that those GPU resources that we mentioned in the previous slide are called textures, the usual name given in GPU land. The way they are used, basically, imagine that this is a texture, is a video, is an image. We're going to command the GPU to fetch information out of them, to put them here in some kind of intermediate stuff, and use that to create the frame buffer. And again, this happens at like up to 60 hertz. The fact that we have to read all this information via the texel fetch or the texture sample implies that there's a lot of back and forth reading from the memory where the video frame is, and then writing back into the frame buffer, and then scanning it out into the screen and all that stuff. That's a lot of bandwidth. So just to give an example, a 4K video frame in RGBA at 60 hertz, for example, this guy that needs to be read and put out onto the screen 60 times a second is almost 15 gigabits per second. So that's a lot of memory. And this is a bit naive because, of course, the texture is not simply sample pixel by pixel to be put into some kind of like part of what is going to become the screen or the next frame buffer, but it will have some filters, some anti-aliasing filters, maybe whatever it is, and that will increase the amount of accesses that we have to this texture by 4x, 16x, 128x. So basically, we'll just incur into a lot of memory accesses. So yeah, and in particular, the video frames, as we saw, there's all these reference frame systems that we have to do. So the video frames have to be kept alive after they have been already presented to the user, so they can be used as reference frames for later delta. I had this beautiful image here from the Wikipedia that says basically video frames are not stored in RGBA format. That is a bit naive. They are stored in YOB format, the YOB encoding. It's great because it allows us to do some subsamplings without any visual quality degradation for the user, and it saves half the bandwidth, which again is a very extreme resource. So let's go to the next slide about the accelerated video decoding. So as we said, accelerated video decoding is the video decoding itself is a very expensive, computationally expensive process, especially on mobile devices, which have small cores usually, and they are battery powered, so power consumption is very important. For this reason, the system-on-chip manufacturers, so people like Intel and MediaTek, for example, Qualcomm, they provide accelerated video decoders, which is a piece of silicon. This area here is a block diagram, very coarse of a modern days system-on-chip. The SoC manufacturers will provide this piece of silicon called the accelerated video decoder that is basically supposed to do better than software at the task of accelerated video decoding. They are sitting either next to the GPU, because when you decode video, you're usually going to be doing something with it in the lines of putting it on the screen, or very close to it. It doesn't necessarily need to be together with the GPU plane, but they're always going to be connected with a high-speed memory bus. Remember the video decode we saw before, similar to the compositor. What it does is to delegate to the vGPU process to talk to this accelerated video decoder via some platform API so that it can happen. One of the differences, of course, is like when all these encoded chunks are sent to via the vGPU process to the accelerated video decoding, the renderer stops seeing the video frames themselves, and what it has is handles to video frames. So if this was a texture in the GPU, then this guy is going to be some reference to the texture. These video frames that are being decoded and stored in some memory level, some cache, some external memory in the system, are of course becoming like very many different formats depending on the vendors and the platforms, and they have very peculiar access restrictions, like perhaps the accelerated video decoder can read it while the GPU can only write to it or something, and very many hours, engineering hours are into making sure that there is a lot of performance going into that. And note is that as you starting to see probably at this point, you cannot talk about accelerated video decoding without understanding how the GPU and the display controller work and how the whole system is going to architect accesses to them. This is an example of a photolithography chip, photolithography die chip picture, excuse me, a die picture taken from a photolithography of an Intel core. This is what is called the Gen 9.5 GPU, and this chip in particular is a Kaby Lake. That is the one we found, the one you could find in the Pixelbook Chromebook that is internally called Eve, or in the Pixelbook Go, which is internally called. There we can see basically what I was referring before. The CPU, there's a giant bus to interconnect everything, there's some caches, there's the display controller, and there's the memory controller. And here in the GPU, this area that is selected over here contains the what Intel calls fixed function, which is all these accelerated video decoding and accelerated video encoding hard-coded parts. I think is this guy over here could be perfectly the encoding, this one could be the decoding, and this is probably the command streamers and the texture fetchers and stuff like that, but we don't know exactly. That's a bit speculation at this point. You can also see, for example, all these regular patterns. These are the GPU execution units. So yeah, an important topic about the accelerated video decoding, when you take a look at that and say, and notice that there's a lot of memory constraints that go into the system, is how we do buffer management. The way video decoding works in Chrome, on ChromeOS, similar to other platforms in this case, is that when the accelerated video decoder needs some resource to decode the video, the next video frame onto, it will go via the so-called DRM KMS API that Stefan Marchesin introduced, I think yesterday as well in ChromeOS Graphics 101. This accelerated video decoder goes via this API, and it decides, it asks if it can give it a next, if it can give a buffer to decode onto. Let's assume this is a keyframe for simplicity. It gets a resource, starts decoding, and hopla, it decodes the first frame. Once the decoder produces a video frame, it's left back in memory. It could be already there. And then the GPU silicon, the plane, starts fetching it to produce the next frame buffer. In this particular case, I'm only displaying something very simple, but it could take quite a bit of time to produce it. Meanwhile, the accelerated video decoder is creating another, is requesting another resource to decode on to start decoding the next frame, possibly using the previous one as reference. And then basically, our friend the GPU will start scanning out to the user while the accelerated video decoder is piling up here again in this memory that is accessible to the rest of the components of the system, the next video frame that is being decoded. Note that the original one, we still have to keep it around as reference frame. Whenever that stops being a reference frame, we can just drop it, and then everything comes back to this pool of resources, and we can continue on. So as you can see, more topics. Oh yeah, one of the stories here, I overly simplify a bit, like when I said memory controller or caches, because normally a system like the one we saw before, the Intel one, will have at least 3 levels of cache, and last level cache, and then some external memory. So these video frames are going to be found somewhere in the system, hopefully in a really close to the CPU and the GPU. Yeah. So a bit of an aside is, of course, adaptive streaming, which is a hot topic the last few years, is basically instead of serving a single resolution to the users, adaptive bitrate is a technology that is implemented in browsers extensively that monitors the buffer health and the playback health so that this guy over here, the head of the network server, can serve to these heterogeneous devices and for the different moment in time, either low, medium, or a really, really great quality, typically by increasing the resolution or the frame rate or both. These resolution changes are typically line up with a keyframe. So you basically get a new keyframe that is larger, and you start again decoding delta frames from that point, but not necessarily. And oh, part of this slide didn't load. That's bad. Okay, that was sad. Well, the software protocol stack is basically how we glue things together in ChromeOS. The render process uses Mojo to talk to, again, remember that we mentioned that before, the GPU viz process. That GPU viz processor inside that GPU process leaves another chunk that is called the Mojo media. It's another talk about IPC 101 where Mojo is described in more detail. In that Mojo media is common for all video decode accelerators on Chrome. And in particular on ChromeOS, we use two different APIs. So this Mojo Media has connectors to these platform APIs. One is called vAPI, the other one is v402. vAPI is an open source specification from Intel that we use to access accelerators on Intel and on AMD. And v402 is basically the API in the kernel. It's a user space kernel API that we can access from Chrome to produce all the hardware accelerator video decoder commands and to get that ball rolling. The API, again, is for Intel and AMD, and v402 is the one we use on ARM platforms. So Qualcomm, MediaTek, Rockchip, and some old NVIDIAs that we don't support anymore. So it loaded. So an aside is what's accelerated in my platform. It's kind of complicated to know, like, for your platform, your OS generation, with all the driver bugs and stuff, what is supported. For that, developers of the future can go to Chrome GPU, and then in Chrome GPU there is a section that is called Video Acceleration Information, and then you can see explicitly what is supported for decoding, also what is supported for encoding, incidentally, and the expected resolution. So code, if you want to decode H.264 and you go above 4K by 4K pixels, this is not going to work. And I think that's basically all I had prepared. I'm sorry about some of the slides not really showing up their content, but thanks. And maybe we can go to questions now. All right. So I think I had some backup slides. No, but I'll just upload them together, but I don't think they're so interesting. Okay, so thanks for listening, and leave comments, upload seals.